And we're back. Video camera battery needed to be recharged. So where were we? We were setting up the mean value theorem where we got this. We're thinking of the nth iterative f as a function to which we're applying the mean value theorem. So if you do the function to x and y, and you can compare that to the x and y before you applied the function, in terms of the ratio would be that derivative of some point in between. So that's what the setup was for where we were going there. Since the C is for some point, as the mean value theorem says, in the interval x and y, we have this result for all points in that interval x and y that we know that the derivative of the nth iterate function at that value of C is greater than lambda to the n. Right? That was the result that was right there for everybody in lambda, and we've decided that that C is in that interval. Since we assume that there was a whole interval, then since we have an interval, the mean value theorem applies. So the derivative of that nth iterate function for anybody in there is bigger than lambda to the n. So in particular, it's true for C. But the C, that's what had fallen out of our application of the mean value theorem right there. So that means that we can change this to the nth iterate applied to f minus the nth iterate applied to y. How far apart those two folks are is greater than lambda to the n times how far apart x and y were before. But the whole choice of n that we made a few lines back was to make this exact product greater than 1. So notice what we have here is the distance between the nth iterate function applied to x and the nth iterate function applied to y. The distance between those two resulting points is greater than 1. So that means after we start with x and y within this set lambda, when you iterate the function applied to them n times, their distance apart is greater than 1. Well, that means at least one of them has to be outside our interval 0, 1. Because if they're more than 1 unit apart, if one of them's inside, the other one's got to be outside. And that's a contradiction. Because that says that x and y, one of them has to get outside, but the assumption was that x and y were in lambda, and lambda is the set of all points that don't go outside. So that's got to be a contradiction. So what led to that contradiction? The only place that we assumed anything. We assumed that there was a whole interval, and that whole interval of points between the x and the y are what allowed us to use the mean value theorem and come up with that contradiction. And so since that assumption is what led us astray and everything else was valid, then the assumption must be false. So that means we've just proven property number 2 from that list of properties for something being a Cantor set, that the lambda contains no intervals. We already had that it was closed. Now it contains no intervals, so that means we have one more piece to show. And that is we need to show that it's perfect. And to show that a set is perfect, we need to show that every point is a limit point of points in the set. And so then the observation that's going to be helpful here is that any endpoint of a sub k at any level of going through the construction of those a's, any of those endpoints is in lambda. Because when you iterate those, what happens is that endpoints go to endpoints, which ultimately go to 0. There it is. And if you go to 0, then that's part of the set lambda, and you stay in lambda forever. you stay within the interval 0, 1 forever, and so that means that the endpoints of those AKs are in lambda. That's why we talked about letting the construction was that those were all open intervals that we were throwing away. So, what do we need to do to show that this is perfect? The set lambda is perfect. Let P be a nice generic point, P for point, in the set lambda. What we want to show is that P is not isolated in lambda. So that's another way to say perfect. That no point is isolated. So if this is a generic point, we need to show that a generic point is not isolated. What does isolated mean? Well, they throw that at you in the text without really giving you a good definition. So a point is isolated. Well, a point P is isolated in lambda. It's about the point and it's about the context. A point is called isolated in there in a set if there exists an open interval about the point P, and that interval contains no other points in, well, okay, I should define this generically, right? A point in general is isolated in a set S, say for any old set S, and then we're going to apply it to our context in a minute. So a point P is isolated in a set S means that there's an open interval around the point P that contains no other points in the set S. So that there can be an interval around it in which there are no other points in S, and that's why it's called isolated. It's isolated from all the other points in S. And so what we want to show is that P is not isolated. And so what we're going to do is the approach we used before. Assume P is isolated. And in our set now is, we are actually trying to show it about our buddy lambda. That's what the whole proof is about, right? So we're going to assume that P is isolated and find out ways that we can do that. That we can draw in the conclusion. So if P is isolated in lambda, and what that means is there exists a neighborhood of P that contains with no other points of lambda inside. I have to do a little battery charge. I'll be back.